So here we want to find the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Over here I drew a little picture of what we're trying to solve. So we're trying to solve for the area underneath the graph of the function. Okay, but in order to do this, let's remind ourselves what the absolute value of 2x minus 1 actually is. So the absolute value of 2x minus 1 is equal to 2x minus 1 if x is greater than or equal to 1/2, and negative 2x minus 1 if x is less than 1/2. Okay, remember that's because if x is smaller than 1/2, 2x minus 1 would be less than 0, and so we multiply by negative 1 to make it positive, because the absolute value is always positive. And so we can break up our integral. Our given integral up here can be rewritten as the integral from 1/2 to 2 of 2x minus 1 plus the integral from 0 to 1/2 of negative 2x minus 1. And again, both of these integrals are with respect to x, so let's throw in a dx in there. And let's rewrite this. So this is the integral from 0 to 1/2. I'm flipping these around just for the sake of simplicity. The integral from 0 to 1/2 of 1 minus 2x dx plus the integral from 1/2 to 2 of 2x minus 1 dx. And so we end up with x minus x squared evaluated from 0 to 1/2 plus x squared minus x evaluated from 1/2 to 2. So if we go ahead and solve those, we end up with 1/2 minus 1/2 squared minus 0 minus 0 squared plus 2 squared minus 2 minus 1/2 squared minus 1/2. So let's go ahead and simplify all this as best we can. We end up with 1/2 minus 1/4 minus zeros, so that's really convenient. We can ignore those. Plus 4 minus 2 minus 1/4 minus 1/2. And so this all simplifies out to be 5/2. Let's move on to something a little bit different. Marginal analysis. Remember that given a profit or revenue or cost function P of x or R of x or C of x, the marginal profit is dP dx. So it's the derivative of profit with respect to x. Respectively, it's the derivative of revenue or cost with respect to x. And so that means the profit function itself, P of x, is just the integral of the marginal profit plus some constant c. Remember, because the integral undoes the derivative. All right, with that in mind, let's take a look at an example. So this example says the marginal profit for a particular item is given by dP dx equals negative 0.005x plus 12.2. And we want to A, find the change in profit when sales increase from 100 to 101 units, and B, find the change in profit when sales increase from 100 to 110 units. So what we're really asked to do is find P of 101 minus P of 100, and we're also asked to find P of 110 minus P of 100. But this P of 101 minus P of 100, is just almost definitionally the integral from 100 to 101 of our marginal profit function. So it's the integral from 100 to 101 of dP dx dx, and over here we have the integral from 100 to 110 of our dP dx dx. And so we end up with the integral from 100 to 101 of, what was our function again? Minus 0.005x plus 12.2 dx. And then here we have the integral from 100 to 110 of negative 0.0005x plus 12.2 dx. Okay, I'll save us all some hassle going through that. What we end up with is negative 0.00025 x squared plus 12.2x evaluated from 100 to 101. And then similarly, we also end up with negative 0.00025x squared plus 12.2x evaluated from 100 to 110. I'll throw on some closing parentheses here. And if you plug those numbers in and subtract, what you end up with is your answer for A is $12.15, and your answer for B is $121.48. All right, let's go ahead and talk about average value of a function. So this is something I'm going to skip over the explanation of because you should have already watched the 2, 3 blue, 1 brown videos, which explain this pretty perfectly. Let's just look at a quick example. It says the world population P in billions from 1951 to 2000 is modeled by P equals 0.0004 t squared plus 0.053 t plus 2.49, where t is between 1 and 50. Where t is the year with t equals 1 corresponding to 1951. Find the average population of the world from 1951 to 1975. As you recall, to find the average value of a function, you take 1 over b minus a times the integral from a to b of f of x dx. And so in this case, we end up with 1 over 75 minus 51 times the integral from 51 to 75 of p of t dt. And so let's go ahead and write that out in more detail here. That's 1 over 24 times the integral from 51 to 75 of p of t. Remember, p is 0.0004 t squared plus 0.053 t plus 2.49. And if we end up solving that, what we'll get is 1 over 24 times 0.0004 t cubed over 3 plus 0.053 t squared over 2 plus 2.49 t evaluated from 51 to 75. So that ends up working out to be 1 over 24 times 78.3792, which yields 3.266 billion people. Can't even spell people right. Billion people. All right, let's go ahead and look at a brief aside. Let's talk about even and odd functions. An even function is a function f of x such that f of negative x equals f of x. So a good example is x squared, because negative x squared is the same as x squared. So for example, 2 squared equals negative 2 squared. They both equal 4. An odd function is one such that f of negative x equals negative f of x. So a good example is x cubed, because negative x cubed equals negative x cubed. So for example, negative 2 cubed equals negative 2 cubed. They both equal negative 8. And that's useful for one reason. If f is an even function, the integral from minus a to a of f of x dx is 2 times the integral from 0 to a of f of x dx. And lastly, if f is odd, the integral from minus a to a of f of x dx always equals 0. So let's say we want to calculate the integral from minus 2 to 2 of x squared dx and the integral from minus 2 to 2 of x cubed dx. The integral from minus 2 to 2 of x squared dx, that's going to be the same as 2 times the integral from 0 to 2 of x squared dx, because x squared is an even function. And so that's going to be 2 times x cubed over 3 evaluated from 0 to 2. So that ends up being 2 times 8 over 3 minus 0 over 3, which ends up being 16 over 3. And lastly, the integral from -2 to 2 of x cubed, well, that's really easy. That's 0 because x cubed is an odd function. Enough of that aside, let's move on back to the actual meat of the chapter. Let's talk about the last part of this section, annuities. A sequence of equal payments made over a time period is called an annuity. Some examples of annuities include mortgage payments, 401ks, and sinking funds. The amount of an annuity is the sum of the payments and the interest earned. If C is the amount paid into an annuity per year, R is the interest rate in decimal form, compounded continuously, and capital T represents the term of the annuity, i.e. the duration, then the amount of the annuity is amount equals e to the r times capital T times the integral from 0 to capital T of C times e to the minus r lowercase t dt. And in here, this should be a lowercase t. So note that this lowercase t here, that this lowercase t and this uppercase t are different things. The uppercase t will be given to you. It's the term of the annuity, and the lowercase t is the variable. With that in mind, let's take a look at an example. So let's say you deposit $2,000 a year for 15 years into an individual retirement account, often shortened to IRA, paying 5% interest. How much will your IRA be after 15 years? So our R, our interest rate, is 0.05 because we write it in decimal form. Our capital T is 15 years, so capital T is 15, and our C is $2,000 because we deposit $2,000 a year. With that in mind, let's put everything into our given function. So we have e to the 0.05 times 15 times the integral from 0 to 15 times c, which is 2,000, times e to the minus r, which is 0.05, lowercase t, dt. And we need to solve this. This ends up working out to be 2,000, because we can always pull the constant out, times e to the 0.75 times negative e to the minus 0.05 t over 0.05 evaluated from 0 to 15. So again, that's 2,000 times e to the 0.75 times minus e to the minus 0.05t over 0.05 evaluated from 0 to 15. And if you plug that into a calculator, you'll end up with $44,680.00.